Hallo, it's Dumplet here. Here's an item on number theory. In the number sequence below, how many perfect squares are there? 2022, 6066, 10,110, 14,154, and so on. Now this item came from the DAM 2022, an examination that Dumplet has hosted. The link to the PDF file will be in the description. Right, so this was one of the easier questions on the exam, and I think it's pretty interesting because, well, perfect squares, and we have a number sequence. So, well, we have a sequence, so maybe we try to find out what's the pattern first. So let's try to analyze the sequence. All right, the first number is 2022, and the next number is 6066. Now the first two, I guess, is pretty obvious. That's 6066. It's just 2022 times 3. And, well, the 10,110, you guys could try to realize that this is 2022 times 5. And, well, I could kind of rewrite this as 2022 times 1. So, well, based from our analysis over here, maybe we could have like a pattern here. It's 2022 times something. So 135. So apparently based on the pattern, it should be multiplied by 7 in this case. And yes, indeed, it's going to be 2022 times 7 for the next term. So there we have it. I think the pattern of this number sequence is going to be 2022 times just like I'm going to say the nth odd number, right? The nth odd number. That's going to be technically the a sub n, or the nth term of our number sequence over here. Okay. Now we just have to find perfect squares that have this general format. So let's try to take a look at perfect squares. And so 2022 times odd, that's essentially just the format of all the terms in this number sequence. And let's try to take a look at some of the perfect squares. Now, in particular, I'm going to take a look at the prime factorizations here. 4 is 2 squared. 36 is 2 squared times 3 squared. 144 over here is 2 to the 4th times 3 squared. And then the 400 over here, the 400 over here, it's 2 raised to the 4th times 5 squared. All right, so you guys could see from the highlight over here, I highlighted the exponents, and perfect squares, they generally, in the prime factorization, not generally, all perfect squares, when expressed in prime factorization, the exponents must be even. And it kind of makes sense because, well, if I were to take the square root of it, all the exponent must be divided by 2. If it's a perfect square, it's an integer, the root is an integer, so I should be able to divide the exponent by 2. So you can have that reasoning as well. Okay, now, so let's try to take a look at the prime factorization of numbers of this format, the 2022 times odd. So the odd number, I have no idea what that is, so let's just skip it for now. And let's try to factorize 2022, all right? Now this number is obviously divisible by 6, right? Because it's divisible by 2, and the sum of its digits is 6. It's divisible by 3, so it must be divisible by 3. And in fact, it's 2 times 3 times 337. Now, for the 337, it might take a while for you guys to verify if it's prime or composite. But then again, you can try to use the sieve of Eratosthenes to help you simplify this one. So the sieve of Eratosthenes tells you that you just have to check for prime numbers less than the square root of 337. Sorry, less than or equal to the square root of 337. Eratosthenes. All right. So the square root of 337, that's less than 19. So I just have to check for prime numbers less than 19. So you can kind of check 337 is not divisible by 2, by 3, by 5, by 7, 11, 13, and 17. It's not divisible by any of those. So by the sieve of Eratosthenes, we're done. 337 is prime. Okay, now going back here. All right, so perfect squares should have even exponents in the prime factorization. Now, this is not the complete prime factorization yet, but, well, take a look at the 2, 3, and the 337. They're all raised to a power of 1 as of now. So this odd number here should allow these 3 exponents to become an even number. Now, the 3 and the 337, that's no problem. I could make this odd number like 3 times 337 to make these 2 exponents become 2. in the resulting prime factorization. But the problem is actually this 2 over here. 2 raised to 1 times an odd number. Well, this odd number doesn't have any 2s, so there's no 2s here, so it's impossible for this 2 raised to 1 to reach an exponent of something even. But if it's not possible for this to become an even number, the exponent here to become an even number, there should not be any perfect squares in this number sequence. And that's pretty much enough for the proof here. And in fact, you could try to check everything here. Because all of these are 2022 times somethings, all of these are actually 2 mod 4. It's divisible by 2, but not by 4, and that's actually enough to become a proof here. Because, well, quadratic residues, let's try to check perfect squares here. So x squared cannot be 2 mod 4. It can only be 0 or 1 mod 4. So if we're going to talk about the quadratic residues, under mod 4, it's only 0 and 1. Alright, so anyways, that's pretty much it. Hopefully you guys learned something new from this video, and I'll see you in the next one. Bye bye!